So as promised, let's find all the homomorphisms from the group Z mod 15Z to Z mod 3Z cross Z mod 2Z. Because the orders of elements in the codomain really is what determines whether a certain map is well defined, whether there is a homomorphism that maps a generator to that given element, let's compute the orders of elements in this group. So this group has 6 elements, and let's just list all the orders here. So first of all, of course, there's the identity, which has order 1. And then 1 plus 3z, comma 2z. What's the order of that? Let's just add this to itself. So if I add it to itself, I get 2 plus 3z, again 3 plus 3z. So I use this element 3 times, 1 plus 3z plus 1 plus 3z plus 1 plus 3z to get to the identity, so the order is 3. Similarly, 2 plus 3z, comma 2z. Okay, 2 plus 3z plus 2 plus 3z is 4 plus 3z. And I add it again, and I get 6 plus 3z, which is 3z. And of course, the second coordinate just stays 2z. So the order here is also 3. Okay, let's try now changing the other coordinate. So that's 1 plus 2z paired with 3z. Okay, I add it to itself, and I already get the identity. So the order here is 2. Let's try 1 plus 3z, comma 1 plus 2z. All right. Okay, so to get the identity on the first component, I need to add this element at least 3 times. So the order is divisible by 3. On the other hand, to get the identity on the second component, I need to add this at least 2 times. So the order is also divisible by 2. So the order of this element is actually 6. If you add it 6 times, that's where this will become 6 plus 3z, and this will become 6 plus 2z, and that's the identity. And finally, 2 plus 3z, comma 1 plus 2z, similarly you compute the order is 6. Even though I don't really care for this at the moment, there is an immediate conclusion from here. The order of this element, 1 plus 3z, comma 1 plus 2z, is 6, which is the same as the order of the group, which means that this group is cyclic. That might seem surprising at first, because we've seen direct products before, like z cross z mod 2z cross z mod 2z, they weren't cyclic. But this group actually is cyclic. And here are the 2 possible generators, right? This one, sorry, no, wrong one, that's not a generator. This guy here, without the brackets, and this guy here are possible generators. I mean, there are generators. Okay, so I could write this as, let's say, 1 plus 3z, comma 1 plus 2z. Let's say cyclic group. But for finding all the homomorphisms, it doesn't actually matter. All that matters is the orders. Okay, so going along our usual lines, so there exists a homomorphism phi from Z mod 15Z to Z mod 3Z cross Z mod 2Z, such that phi of 1 plus 15Z, which is a generator, is equal to H if and only if the order of H divides 15. Okay, so I look at these numbers and I look at those that divide 15. 1 divides 15, 3 divides 15, 3 divides 15, 2 doesn't divide 15, 6 doesn't divide 15, and the other one also not. So how many different elements can I send 1 plus 15z? I have 3 options. So there are three homomorphisms. The 3 homomorphisms, let's call them phi Maybe 0, 1, 2, I don't know. Maybe that's a good idea. From Z mod 15Z to Z mod 3Z cross Z mod 2Z. And what are they given by? So phi I of 1 plus 15Z would be, okay, so I can map it to this element, to that element, and to that element. That's why I used I. So it's I plus 3Z, comma 2Z. Right, so phi 0 would map 1 plus 15Z to 3Z, comma 2Z. So phi 0 is the zero homomorphism. Phi 0 is the trivial homomorphism. Phi 1 is going to map 1 plus 15Z to 1 plus 3Z, comma 2Z. And then phi 2 will map 1 plus 15Z to 2 plus 3Z, comma 2Z. If I were to look at kernels and images, so of course kernel of phi 0 is the entire group Z mod 15Z, and the image is just 3Z, comma 2Z. But let's look at kernel of phi 1. So which elements in Z mod 15Z are sent to the identity here under the phi 1 homomorphism? So phi 1 sends 1 plus 15Z to 1 plus 3Z, comma 2Z. So, well, of course 0. But what else? So 1 plus 15Z goes to 1 plus 3Z, 2Z. 2 plus 15Z is going to go to 2 plus 3Z, 2Z. So 3 plus 15Z is going to go to 3 plus 3Z, which is 0, comma 2Z, which is 0. So 3 plus 15Z. And similarly, 6 plus 15Z, 9 plus 15Z, and 12 plus 15Z. Okay, so that's the kernel. What about the image? Which elements do you get? The image is actually, you can get everything here, right, on the first coordinate, but always 2Z on the other coordinate. So I would just write A, comma 2Z, where A is anything in Z mod 3Z. Right, I mean, it's just for you to remember, the kernel is a subgroup of the domain, while the image is a subgroup of the codomain. Let's do another one. Using this group, I kind of like it because it's actually a cyclic group, and I wanted to say something about it, therefore. But I want to change this here. And I'm going to change it to mu6, so the sixth roots of unity. Okay. So, one comment before we move on with this. One comment that just follows from what we discovered, that namely that this is a cyclic group. So, comment, note, as Z mod 3Z cross Z mod 2Z is a cyclic group of order 6, we get that it's isomorphic to Z mod 6Z. Because every cyclic group of order n is isomorphic to Z mod nz. What do we know about this group? Is that group maybe cyclic? Yes, right? It's generated by zeta 6, where zeta 6 is cosine 2 pi over 6 plus I sine 2 pi over 6. Oh, so it's also a cyclic group. And how many elements does it have? Also 6. So this group is also isomorphic to Z mod 6Z. So similarly, so also as mu6 is a cyclic group of order 6, we get that mu6 is also isomorphic to Z mod 6Z. Because isomorphism is an equivalence relation, then we also get that, of course, mu6 is isomorphic to that group as well. So look, there are three different groups, three different things that arise differently. This arises as a direct product of two groups. This arises as congruence classes mod 6, and this arises as 6 roots of unity. But from the point of view of group theory, if somebody uses just that telescope that allows you to see, that does not allow you to distinguish between isomorphic groups, then there's no difference from such a person between this, and that. Okay, why do I say it's not quite relevant to the question? Because I actually don't want to know whether there exists an isomorphism between this and that, which is what that proves. I actually would like to know what it is and also what the other homomorphisms are. So I want to know all the homomorphisms. So let's get to work. So for that, we need orders of the elements here, but we already know, right? We know the orders of elements in Z mod 3Z cross Z mod 2Z are 1, 2, 3, and 6. We listed all the elements, and these were all the possibilities. And by the proposition, so by proposition 4, there exists a homomorphism phi from mu6 to Z mod 3Z cross Z mod 2Z such that phi of zeta 6 is H if and only if the order of H divides 6, right? 6 is now the order of this group. But what are the orders of elements here? 1, 2, 3, and 6, they all divide 6, which means I can really send zeta 6 to any element here, because any element here has order that divides 6. So as 1, 2, 3, 6 all divide 6, there exist 6 homomorphisms. I'm going to denote them by phi AB from mu6 to Z mod 3Z cross Z mod 2Z. And my phi AB is going to be defined by the fact that it takes zeta 6 to A comma B. So let's actually look at some of these homomorphisms. I will not need this proposition anymore, so let me erase this. Let's look at them. So first of all, the first homomorphism I want to look at is phi. So how about 3Z, 2Z? Okay, so that's a homomorphism from mu6 to Z mod 3Z cross Z mod 2Z. What does the homomorphism do? According to the definition, it takes zeta 6 and maps it to 3Z, 2Z. Oh, that's the 0. I mean, that's the identity in this group. So zeta 6 is mapped to the identity. But that means now every power of zeta 6 is going to be mapped to the identity, right? So, phi of 3z, phi 3z, 2z of zeta 6 to the n is, okay, so I can take the power outside, but taking the power outside, I'm acting now on this group, and in this group, I shouldn't really use exponentiation, I should use multiplication instead. So I get that this is n times 3z, 2z. Oh, but that's still 3z, 2z. So phi 3z 2z is the trivial homomorphism. So in particular, its kernel is everything, mu6, and its image is just 3z comma 2z. Let's look at another one. Let's pick something. Let's pick maybe 3z 1 plus 2z. What does that do? So that's from mu6 to z mod 3z cross z mod 2z. Let's see. So I know by definition where this guy takes zeta 6. It takes it to 3z comma 1 plus 2z. So where will it take zeta 6 to the power n? So an arbitrary element of mu6. Well, that's again, so the n comes out, but here the operation is addition, so I'm just going to write it like this. So that gives me, well, n times 3z is still 3z. But here I get n plus 2z. Okay, so I get a formula that tells me where every sixth root of unity goes. So I can compute the kernel. What is it? Which elements are taken to the identity? Of course, you are taken to the identity if and only if n is even. So that's 1 zeta 6 squared and zeta 6 to the 4th. Now, if you remember your roots of unity, you know that that's the same thing as mu3, the cube roots of unity, which is, by the way, a subgroup of mu6. So the kernel of this homomorphism is exactly the cube roots of unity that sit inside the sixth roots of unity. What's the image? Well, what can you get? You always get 3z on the first component. And you get, well, the only two different things are that you can get is 0, 1. So you get this subgroup of z mod 3z cross z mod 2z. Okay, I'm not going to analyze all 6, but let's do another example, different from the others. So let's do phi 3z comma, let's do phi 2 plus 3z comma 1 plus 2z. What does that do? And because I kind of don't want to keep rewriting this long subscript, I'm just going to call this psi. So when I say psi, I mean phi 2 plus 3z comma 1 plus 2z. So that's a map from mu6 to z mod 3z cross z mod 2z. And what does the map do? So psi of zeta 6 is 2 plus 3z comma 1 plus 2z. All right, let's then compute. So we can, of course, compute the general formula. So psi of zeta 6 to the n is 2n plus 3z comma n plus 2z. Right, because the n comes out, so it's just this added to itself n times and this added to itself n times, so you get that. But in particular, let's just, in this case, let's actually compute all the values of this particular homomorphism. So zeta 6 squared will therefore be 4 plus 3z, so in other words 1 plus 3z, comma 2z. Right? Squared gives you twice that, so that's that. Cubed, which by the way that's minus 1, right? Zeta 6 cubed is minus 1. So where does this go? So I'm putting 3 here, so it's actually 6 plus 3z, so that's 3z, comma 1 plus 2z. Let's do zeta 6 to the 4th power. Well, that's again 2 plus 3z, 2z. Psi zeta 6 to the 5th power is going to give you 4 plus 3z, so 1 plus 3z. 1 plus 2z. And of course, zeta, psi of zeta 6 to the 6th power, which is just 1, is 3z, comma 2z. All right. Okay. What's the kernel? Which elements, which power of the 6th root of unity, the 6th root of unity is, the zeta 6 is mapped to the identity? Only one of them, only one. Just one element in mu6 is mapped to the identity in the other group, so the map is injective. And what's the image of phi, of psi? Which elements do I get? I think I get everything, right? Here's the identity, then everything with 2z on the second component. 1 plus 3z, 2 plus 3z, 3z, and then everything with 1 plus 2z on the second component. I get 3z, 1 plus 2z, 1 plus 3z, 1 plus 2z, 2 plus 3z, 1 plus 2z. So I also get everything. So the map is surjective, right? The image is everything. So psi is surjective. Hence psi is an isomorphism. Hence psi is an isomorphism. Note that if you were doing this computation, suppose I gave you such a long problem, and you came up with all the homomorphisms, there are 6 of them, and you computed the kernel of image of every one of them, and you somehow got that none of them was injective, you would have known by that time that you've made a mistake, because you know that the groups, this one and that one, are isomorphic, because they're both cyclic and have the same order. Therefore, at least one of the homomorphisms had to be an isomorphism. So at least one of them had to be both injective and surjective. I encourage you to do more examples of trying to find all the homomorphisms from a cyclic group to a group, and then try to find their kernels and their images and decide which of them are isomorphisms, if any.